Okay, well, let me first apologize for not realizing some of the technology wasn't going to work the way I thought it was. I'm handing out a program for the calculator, and it's a very simple little thing, so it shouldn't take you very long to program. It's real short, uh, which does some numerical approximations. Unfortunately, and I've got it on a calculator, not that's on a USB drive, because I was at home last night or yesterday and put it into that calculator and put it on a USB drive and thought, well, I'll just plug it in here and show it to you. However, the gizmo I've got plugged in that does the recording doesn't leave enough space to plug the other USB drive in. So what I'll do is I will come back and add that in for and do a separate thing that just does that so the in-class people can see it, but I'll put a separate one up for the take-home stuff. So let me talk about it a little bit first. Okay. This the problem situation is this: we have a first order differential equation (ODE). It's an initial value problem because I know what the derivative is. It's f of x, y, and I know what it is at a particular spot. So the idea is, if you look at the picture here, I've got some point x0, y0, and the solution is, we're going to use the book's notation, that's a phi, y equals phi of x, is the honest to goodness solution it's the solution passing through x0, y0. Okay. So I've got a picture of it here. This is my solution phi there. But of course, we don't know what that is. That there is, we know there is a solution. We got a way of checking that out. We don't know what that is. Okay. We'd like to come up with it, but maybe we can't. So what we'll at least like to do is, uh, can we evaluate phi at some, I know what the value of the phi is at x0, y0, but can we evaluate phi um, at some other point, say uh, some value x1? And the answer to that question is no, not necessarily. But maybe we can we approximate the value of phi at some other point? And that's what we're going to do here. We're going to figure out some way of approximating it and then getting better and better approximations here. So the idea is that I have some other x1 out here. And what I'd like to know is, what is the value of the real honest to goodness value of the function at that particular spot? Okay. We don't have a formula for it, so we can't really tell. However, what I do know is I do know what the derivative is at any particular point in the plane. And this is something I kind of talked a little bit about at the end of the period last time, and I'm going to hope to make a little more sense out of it this time. Okay, so the tangent slope at x0, y0 is what you get when you plug in x0, y0 into this f of xy, because that's what dy dx is, that's the tangent. Okay. So I've got the tangent line drawn there as the red line. Okay. And we can use the tangent the equation of this tangent line is y equals, okay, well, it's the slope, f of x 0, y 0, times x minus x 0 plus the y coordinate of the point we know. Okay. Now, I'm not going to be able to find the y value that's on the honest to goodness solution, but if I know the equation of the tangent line, I can find the y value of the point on the tangent line, and that'll be a pretty good approximation as long as we don't go too far. So what we do is we let this distance be, let's call it h. If you go back to your calculus 1, you might have called that dx or delta x. Then the little extra space here. Whoops, that much. Picture. Then the y value then corresponding to x1, we're going to call that y1, which is f of x 0, y 0. Now, x, okay, if I plug in x1 here, this is the distance h plus y 0. And that's an approximation based on the tangent line. And is it a good approximation? Well, if h isn't very big, it's probably not too bad. This is the idea behind the Euler method. Leonhard Euler was a Swiss mathematician. It's not Euler. By the way, the mathematics graduate students at Vanderbilt University, we had a softball team, and we called ourselves the Oilers. Of course, nobody else could pronounce it. They thought it was all Eulers. And as a matter of fact, we won the Summer League Championship, the intramural championship. And I don't know whether you ever watch SEC basketball, but Barry Booker is sometimes on there as a color commentary. He was one of the guards for the Vanderbilt basketball team. One of the forwards was Frank Cornett, and his son was playing at Vanderbilt just like last year, the year before last. So we played in a championship game. We played a bunch of athletes, and we beat them because two reasons. We didn't have a very good pitcher, and that team would not take a walk. Okay, so our pitcher was bad, but they wouldn't take a walk. They had to hit the ball. Also, we had some pretty good outfielders, and there was no fence. So they would knock the ball a mile, but our outfielders would be out way back there, just back up. And all we did was we just kind of slapped base hits over the infield. That's about all we did. And so the math people actually beat a bunch of athletes. And Barry Booker actually borrowed my glove. I was playing first base, and he borrowed my glove, and I don't know how he got his hand in it. But anyway, we were the Oilers. Okay. It was a joke that nobody else got, which is typical math joke. Nobody else gets it. Okay, so anyway, that will give you an approximation. Now, if we wanted to go further, I thought I had a slide for this, but I don't. So here's our real solution, which we don't know. Okay. Here's the point that we do know. And let's say we wanted to find, let's not call it x, let's call it something else, a, I guess. We wanted to find a solution to the value of the honest to goodness solution at this x equals a value. Well, we could do it all with the tangent line all at once, like I had a while ago. But you see this, that a tangent line at this spot that value isn't anywhere close to where it ought to be. Okay, so the error would be considerable if we used that. So what we'll do then is we'll bust up this interval into little pieces and do it one step at a time. In other words, we'll go out one amount at that point, recompute the tangent line, go out on that tangent line, recompute it, go out a little bit on that one, recompute it, go out another tangent line at that one, and so on, and we'll get a polygonal approximation to it. And that's what Euler's method does. And the basic notion behind Euler's method is given here, is that we have our initial value problem. Okay. What we do is we let h equal the step size we wish to take. Now, if all we want to do is in one great big step, we would just let h be like in this case, a minus x0, but we usually want to break it up into smaller pieces. Then x1 is x0 plus h. Y1 is, well, we just had that on the previous screen. It's going to be f of x0, y0, h plus y0. And that would put us, on this graph, that would put us about there. Then we do our next spot. Our next one, x2, would be x1 plus h. So we go out a little bit further. Y2 would be the value of the derivative at x1, y1. Now remember what this thing does is it gives you the slope of the tangent line for all the solutions in the plane. Okay. You just put in an x value and a y value, and it tells you the solution that passes through that point has this particular slope. So y2 would be f of x1, y1 times h plus y1. Okay. And that would, at least the picture I've got here, put us up at this particular spot. We keep this, well, let's do x3 just to make sure we got the pattern here. x3 would be x2 plus h. And then y3 would be f of x2, y2 times h plus y2. And picture-wise, that would mean we go off on this tangent a little bit to another point. Okay. We keep this up then and we get the following recursive relation. Xn plus 1 is Xn plus h. Yn plus 1 would be the value of my slope function at the previous point, xn, yn times h plus the y coordinate at the previous point. Okay, and that's what the program does. Okay, and what I'm going to do, I really should have done this a different way, is I'm going to come back later at the end of the period and work it out for people in the class. And I'll go back later and put in a special extra little video for the online, for our online student. And then right now I want to go into the next section. You can do, this is, by the way, this is really easy to do. You could write a very little simple routine for an Excel program, frankly, and it would automatically increase each x value by the h and then do the computation. So as you see on this Euler program, it's a it's probably simpler. Well, it's a good deal simpler than the slope field program I gave you out. And if you get online and look, there are some other ones that make tables, there are other ones that draw pictures and stuff, but the one I've got is probably as simple as it needs to be, and it does what the book asks for us to do in this next section. Okay, but I'll come back and finish that up later. We need to get into the next chapter when we actually start doing some things. And what I have to do is, well, I noticed this as I was looking through the textbook. He makes a very good point that you really need to be good at integration here. And before we start the technique of separation of variables, he suggests if you're not real good at integration that there are three techniques in the back of the book that you should make sure you review. And we're going to review them. One of them everybody has seen, which is substitution. And basically what that means is you change your variables a little bit so that your integrand matches a form that you know already. And by the way, if you don't have that calculus book I put online, or if you don't have a good calculus book, you really ought to get one. You're going to need it for sure in this section. Okay. Let me see if I got my example here to do. Somewhere, yeah. Let's see, can you integrate the integral of x times cosine of 3x squared dx? Okay. Well, this is a substitution problem, and you recognize that the x, well, there's a 3x squared inside of the cosine, and the derivative of 3x squared is 6x. In other words, it's just an x. So maybe you can use this x that's out in front with the dx. In other words, I'm not saying this very well, but the substitution, if you let u be 3x squared, then du is 6x. Remember to put a dx on there. Now, we don't have a 6x dx, but we do have an x dx. And different people do things different ways, but the way I like to do it is to make my substitution stuff exactly match what's inside the integrand. In other words, I have an x and a dx, and that would be 1/6 du. Some people would multiply on the inside by 6, on the outside by 1/6. You may have learned it that way. But that's not how I learned it. X dx is 1/6 du, and the cosine of 3x squared is cosine of u. This is something you can integrate because it's just a plain old cosine. With the 1/6, the constant comes out there. The antiderivative of cosine is the sine. Now, the derivative of cosine is minus the sine, but the antiderivative is just plus the sine. And then, of course, we pick up some constant. And we've done the calculus. It's just now it's our turn to substitute back in because we started with the function of x. We need to end with the function of x. So 1/6 sine 3x squared plus c. Okay, that's an example of substitution. Let me do another one just to make sure we got it. This one's a little more interesting. X times the square root of x plus 4. There's probably I think there's maybe two ways to do this, but I can do the integral of just a plain old square root, because that's an x to the 1/2. You just add the power, 1 to the power. But when you've got an x plus 4, that complicates things a little bit. So that suggests what the substitution could be. Let u be x plus 4. Okay. Then du is just plain old dx. That's good. Now, so that's going to give me that much. And the x out in front is, if u equals x plus 4, then u minus 4 equals x. So you can't mix your variables. You got to write it like that, though. So this can be substituted this way, and that's workable if you write everything as powers, because this is u to the 1/2. So when you multiply this out, that becomes u to the 3/2 minus 4u to the 1/2 du. So increase the power by 1. Okay, now the first term, let's see, u to the 5/2, so it's going to be 2/5 of that because when okay, I take the derivative, the 2/5 and the 5/2 is going to cancel it. Okay. Now the next term, the 4 is there already, and u to the 1/2, you have to add 1, u to the 3/2, and then you divide by your new power, making it to 2/3. And at this point, before you simplify things, you just make sure you take a step and check your antiderivatives. It's a 2/3 and a 3/2 will cancel when you take the derivatives. So it's 2/5. Or it's getting a little bit squirrely. So it's 2/5 u to the 5/2 minus 8/3 u to the 3/2. So that's almost, calculus is all done. Let's put our x's back in. Oops. 2/5 x plus 4 to the 5/2 minus 8/3 x plus 4 to the 3/2 plus constant. So there's a couple of substitution problems. Get stranger. They can be weird, and some of them are really kind of unique. But I don't think we'll have to do anything too much harder than that here. The next technique is integration by parts. And it is used lots of times when you have an integrand that has two factors that don't look much alike. And the idea about integration by parts, integral of u dv is uv minus integral of v du. So if you've got an integrand that doesn't really fit some sort of formula, is you need to somehow break it up into pieces, two pieces, where one piece is easy to take the derivative, and the other piece is easy to take the antiderivative. So what I have here is an example. And I said a lot of times it is a problem where you have an integrand with different types of functions. For instance, integral of x sine x is a very typical integration by parts problem. Uh, when I said something's easy to differentiate, I basically mean when you take the derivative, you get something that's nicer than what you started with. That's what I mean, basically. Not necessarily that it's easier than the other, but that by taking the derivative, it becomes, if you take the derivative, it becomes simpler. In other words, on this one, x sine x dx is I'm going to put u equal to x, and dv would be everything else. And why did I make that choice? Well, because the very next step, I take du, that x term has gone away. It's simpler now. And the other reason I chose it is it's just about as easy to take the integral of sine x as it is to take the derivative. So if dv equals sine x dx, then what's v? So take the antiderivative of sine. Well, it's going to be a cosine, but is it going to be positive or negative? Okay. Okay. Take the derivative of this. What's the derivative of the cosine? Minus the sine. I don't have a minus there. So v is going to be negative cosine x, not positive cosine x. But as I said, it's just about as easy to take the derivative as it is to take the sine. Let's take the antiderivative of this. And take it. Okay, so it's uv x minus cosine x minus the integral of v du. So it's negative x cosine x, and then the minus minus makes it a plus cosine, and now we've got negative x cosine x. The antiderivative of cosine is positive sine. The derivative of cosine is negative, but the antiderivative is positive, and then plus cosine. So there's an example of integration by parts, typical sort of problem. Some of them get really, really strange. If you have something like e to the x times sine x, you have to integrate by parts and then do 3 or 4 other things to it and get real clever. I had a professor one time say that that's about the only thing you ever needed to learn out of calculus, integration by parts. Okay, now the last thing though is actually involves about 3 ideas that if you took calculus 2 here and used it out of the book we just finished up, you never saw. Okay, now you saw it in your AP calculus. But whoever chose the old calculus book that we used to use, we don't use it anymore, chose something that was just a bad book. That's why I said get a copy of this thing, the James Stewart book, if you don't have it. But it involves partial fraction decomposition, but I can't even talk about partial fraction decomposition until I talk about trig substitutions. And we're not going to do a whole lot of trig substitutions, but every now and then it might show up. Let me just ask a few questions here. What's the integral of 1 over x dx? It's a natural log, and we don't know where we are, so it might be put an absolute value around. All right. number 2. What's the integral of 1 over x squared dx? Actually, that's probably step number 3. But I'll let let's go with that. Okay, well, this is not a natural log problem. It's just a power rule. Because you add 1 to the exponent and divide by the new exponent, so it'll be negative 1x to the minus 1. Oops. So that's, sorry about that. Negative 1 over x. Try that again. What's constant? Okay. What about the integral of 1 over x plus 1? Okay. Just the same thing as before. Maybe you could do a substitution if you really needed to, but it's same as before. Okay. Now I have 2. Okay. 1 over x squared plus 1 dx, 1 over x squared minus 1 dx. These, especially the first one, are not handled like anything above. The second one is something that we'll do in a second. It calls for breaking it up into 2 pieces by partial fraction decomposition. Okay. The first one is an inverse trigonometric function. So we need to talk about that a little bit. And the biggest problem with that is if you took Calculus 2 out of our old calculus book, it didn't talk about inverse trig functions at all. So here's the, I don't know that I want to talk about it too much. This is the expression we had in that first integrand. There is a right triangle associated with that type of expression. Remember, the right triangle is the sum of the, if you square the 2 legs and add them together, then that gives you the square of the hypotenuse. So if you see 1 plus x squared, that kind of looks like that these are the 2 legs. And they are. Let's put an angle theta here, put a 1 here, and an x, and then the hypotenuse is the square root of 1 plus x squared. Okay, so that's the right triangle that goes with the 1 plus x squared type of thing. If you had, say, a 4 plus x squared, then you'd draw a triangle like because you let one of the sides be 2, the opposite side, and you let the opposite side be x, then the hypotenuse will be the square root of 2 squared plus x squared. Okay. Now, based on, and of course, we'll always put our angle of interest down in the lower left corner. All right, going back to the first triangle. Okay. Okay. The tangent of theta is the opposite over the adjacent, or it's just x. So there's actually your substitution. And as far as the square root of 1 plus x squared, that's the hypotenuse. The hypotenuse over the adjacent is the secant of theta. So if you just squared all of this, 1 1 plus x squared is then the secant squared of theta. Okay. Let me go back and make sure I got the. Okay. All right. So the. Come on, next page. Ah, okay. So what the integral we had is 1 over x squared plus 1 dx. Well, x squared plus 1 plus x squared, same thing. I probably should have. I got it written a little bit backwards here. Okay, now I know what the denominator is because it's right here. So I've got a substitution for the denominator. What is the dx? If x equals tangent theta, what's dx? Well, to find dx, you take the derivative. And what's the derivative of the tangent? Hmm? No, the derivative. Derivative. It's a little bit, it's something that's, it works out nice on this problem. The derivative of the tangent is secant squared. So, get your calculus book out every now and then and make sure you've got these. This particular book I gave you has reference pages in the back with derivatives of your trig functions, inverse trig functions, tables of basic integrals and stuff as well. So the dx is the derivative of tangent is secant squared theta, and now I don't know what the derivative of theta is, so I'll just put d theta. Substituting all of that in then, 1 over x squared plus 1 is secant squared theta. Dx is secant squared theta d theta. The secant squareds cancel. Okay, and you've got the integral of 1 d theta. Well, theta is the variable now. That's going to be theta plus a constant. Clean that up a little bit. Secant squareds, one on top, one on the bottom, they cancel. Okay, so it's just the integral of 1 d theta, theta plus constant. Okay. Well, we started out with x, not with theta. X is tangent theta. To get back at, take the inverse tangent of both sides. Theta is inverse tangent x. One over x squared plus 1 is an inverse tangent. You see a polynomial, you think, well, there's no way it's got anything to do with trigonometry. Well, it does, because it fits into a triangle, and if you're doing anything with triangle, it comes up with trigonometry. Okay, so if you've got a 1 over 1 plus x squared, you can find, okay, they have tables of integrals for something squared plus your variable squared. And if you look through there, you'll see that sometimes it involves inverse tangents, sometimes it involves logarithms. There's a whole lot of stuff going on here. Okay. Well, we do one more. No, I'll come back and do some things in a minute. Okay. Now, that's a different app. You can draw a right triangle that has some sides that kind of match up an x squared minus 1. And do some trigonometry on it. It does not simplify the problem. It becomes a big mess. It can be done that way, but basically when I teach calculus 2, I give people a problem and say do it that way, and after they've struggled with it for a while, I convince them that that's really not the way you want to do it. So we have something called a partial fraction decomposition. It helps us to break up rational functions. And what a rational function is, it's a polynomial over a polynomial. Partial fraction decomposition. You can't read that very well. Now, basically to do this, we have to first have, we're going to assume if you need to, you do long division so that the numerator degree is less than the denominator degree. When you don't want an x cubed over an x squared. So I'm going to assume that that's already done. Then whatever the polynomial in the numerator is, its degree is less than what's in the denominator. Factor the denominator completely. Okay. Now here's where it gets tough. Okay. So this is going to completely means as a product of linear factors. Those would be things like ax plus b to some power, perhaps, and irreducible. No, they spell irreducible. Try this out. Quadratic factors. Okay, now it'll be something like, and I probably shouldn't use, let's use something else, cx squared plus dx plus e, and they might be to some power as well. If the polynomials, the denominator is a real big high degree polynomial, then it's going to factor in. You may have just really messy factors. Okay. Now here's where let's see, I hadn't really planned on doing this till yesterday, so let me see how I want to do this. This is a denominator. Each factor, each of one of these linear factors of the form ax plus b raised to some power will give you partial fractions have partial fractions. A1 over ax plus b, A2 over ax plus b squared plus a sub n over ax plus b to the n. So if you had a linear factor that was cubed, you'll have three fractions. Something with your linear factor, a constant over your linear factor squared, plus a constant over linear factor cubed. Each irreducible quadratic okay, so that's this guy here, and that's cx squared plus dx plus e to some power. Hopefully it's not anything but power, but if it is, you're going to have, we'll have partial fractions. Capital CX plus D, well, let's use capital letters. Capital plus C over CX, little cx squared plus dx plus E, oops, these are all ones here, plus B2x plus C over cx squared plus dx plus E squared C2 squared plus dot 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 plus B sub mx plus C sub m over that irreducible quadratic cx squared plus dx plus e to the m power. The board's out of alignment here. Now, the reason you write these is you may not know it, but every one of these fractional type of things are things you can integrate. So let me do a real simple one. And that is x squared minus 1 in the denominator. Okay. That's a rational expression. It can be factored as x plus 1, x minus 1. And that means I can rewrite it as a constant over x plus 1 plus some other constant over x minus 1. And we have to figure out what those two constants are. And the way we do that is, well, if you were to combine these two, okay, you'd have to get a common denominator. And this would be what your numerator is. This times x minus 1 plus b times x plus 1. That's what your numerator would be, and that should equal the original numerator. So you get ax minus a plus bx plus b equals 1. Now you bust it up because the left-hand side has some x's and the right-hand side doesn't. So the x coefficients on the left have to equal the x coefficient on the right, and there isn't one. And your constant on the left, it's a minus a and a plus b, should equal the constant on the right. These things solve. Fortunately, you just add them straight up. The a's go away. So you get b is 1/2, and what's a? I'd look at the top equation, I guess. A would then, if you look at the top equation here, A is negative 1 half. So now we're ready where we can actually do some calculus. Negative 1 half over x plus 1, the integral of that, well, it's going to be a negative 1 half times the log of x plus 1. And then the 1 half over x minus 1, the integral of that is 1 half log of x minus 1. So, and if you look in the calculus book, there is an integration formula. There's in the integral tables. You can find something that handles this. Well, I'll be honest with you. If you haven't used complicated integral tables, sometimes it's easier just to do the integral. Even a mess like this, sometimes it's easier just to go through all of this than to try to make your integrand fit some generic sort of formula on these. Okay, so let's do one that's a little bit more complicated. Let's do I'm just doing this off the top of my head, so it may turn out to be a big mess. The integral of x plus 1 over x times x squared plus 1. Okay, fits the form. We've got polynomials on top and on the bottom. The degree on top is 1, on the bottom is 3. And there's no simplifying. I can't cancel anything off on this. So we're going to do a partial fraction decomposition. Okay, now the way partial fractions went is for every linear factor, I have some constant over that factor. Now, if it was an x squared, not just plain old x, I'd have an a1 over x and a2 over x squared. But since the x just goes to the power, I only have one fraction of this form. We talked about irreducible quadratic factors in the denominator. I have a fraction of the x squared plus 1, but it has a linear factor on top. Now, and I only have one of these fractions because my x squared plus 1 term, thankfully, is just the first power. If it was squared, I'd have another guy over here, b2 plus x plus c2 over x squared plus 1 squared. And if it was x squared plus 1 cubed, I'd have another one over here, b3x plus c3 over x squared plus 1 cubed. Okay? And those things I could integrate. Okay, so I have to figure out what those constants are, a, b, and c. And we look at what the numerator would be if we combine those two fractions on the right. I've got to get x plus 1 because that's the numerator on the left. It would be a times x squared plus 1 plus bx plus c times x. So x plus 1 would be ax squared plus a plus bx squared plus cx. And now break it down to each term. I mean, the x squared coefficients have to be the same. On the left, there's no x squared coefficient. On the right, it's a plus b. The x coefficients have to be the same. On the left, the x coefficient is 1. On the right, it's c. constants have to be the same. On the left, the constant is 1, and on the right, the only constant term is this a there. Okay, so this works out. C is 1, A is 1, and these two things together say B is negative 1. So 1 over x plus minus 1x plus minus 1x plus C is 1. Okay, and I'm actually going to break this thing up a little more. So now I've got this all written down in terms of fractions, and I can integrate this. It's going to be a logarithm. This one is also going to be a logarithm. And this one is going to be an inverse tangent. So let me just give you the answer, and you can figure that integral of 1 over x is natural log of x. This one's a little more interesting. Minus 1/2 the ln of x squared plus 1. And the last one was, we did a while ago, inverse tangent of x is constant. Okay, so I've still got a few more minutes in class. We'll talk a little bit about the Euler function on the calculator, and I'll get a little 5, 10, 15-minute video presentation figured out and post that along with this stuff. But we're going to be doing some integration. So if this is not something you've done for a while, or you're not real good at it, then get a good calculus book handy, and be looking in particular at those 3 sections: the one on substitutions, the one on integration by parts, and some on the partial fraction decomposition. Okay, so